3 marks or 4 marks question from this part. Okay, so state tables and graphs. The state table and graphs provide a more systematic approach, means the concept of having the state tables and graph, it will provide a systematic way of dealing with the logical circuits. Okay, so it provides a systematic approach which is useful for the analysis of larger circuit, right? So it is used to analyze a larger circuit with a systematic approach. This is possible with the help of state tables and graphs, right? So which leads to the general synthesis procedure for sequential circuits, right? So by having state tables and by having a graph, correct graph, so we can able to generate a larger circuit which provides an easiest way to synthesize that particular logical expression. Okay, the state table specifies the next state and output of the sequential circuit in terms of its present state and input, right? The last sentence, it explains that the state table specifies the next state and the next output of a sequential circuit. Means it will be used to predict the next state and the next output of a sequential circuit with having the present state and present input. Okay, so in the next diagram, there are few information about the state table, right? So the following methods, means the following methodology can be used to adopt for the state table. It says that determine the flip-flop input equation and the output equation for from the circuit. So if I am using any kind of flip-flop, like either it might be D flip-flop, T flip-flop, SR flip-flop, or JK flip-flop, or D with clock enabled flip-flop. So I need to think about what input I have provided to the flip-flop and what will be the possible output for that particular flip-flop. So with the available information or introduction of all the flip-flops, right? So we know that when I consider D flip-flop, so whatever D flip-flop, it says that data flip-flop. So whatever D input, so that will be directly forwarded to output Q. That is what your D flip-flop. And when I consider T flip-flop, the T is equal to 0, output will be equal to 0. When T is equal to 1, output will get a toggle. That is what the output we can predict for the T flip-flop. Similarly, when SR flip-flop, if I consider, because of two inputs, I can say that when SR is equal to 0 and 1 respectively, so it will be in set condition. When SR is equal to 1 and 0 respectively, then it will be in set condition. So that is the output. You can define it with respect to the SR flip-flop. When it comes to the JK flip-flop, it says that when JK flip-flop is equal to 0, 1, then it will be in the reset condition. When it is 1, 0, then it will be in a set condition. And when JK inputs are 1, 1, then it will be in toggle condition. So these are the few information about the flip-flop output stage. Hence, in order to find out the flip-flops, in order to find out the flip-flop input equations and the output equations, it is mandatory to know both input and output equations of the flip-flop, right? So this flip-flop are supposed to be acting as an active element for designing a kind of state graphs and state tables. Okay, next, after knowing the flip-flop input and output equations, the next step, it is used to derive the next state equation for each flip-flop from its input equation using one of the following relations. Okay, so hence, as I said, the D flip-flop has got this kind of facilities. You can copy these equations where it will be provided with a equential, that is the logical equation of all the flip-flops. The D flip-flop will have Q plus, where plus indicates the next state. Q plus will be equal to D for D flip-flop. Similarly, if I consider D flip-flop with clock enable Q plus, that is the next state output which depends upon the combination of D into CE, where CE stands for clock enable, plus Q into CE bar, where CE bar is a complement of clock enable. Next, the characteristic equation of the T flip-flop, for it says that Q plus, that is the next state of the Q plus, it depends upon T exclusive or with the previous output Q, right? So if I write it as only Q, then that will be called as previous output. If I write it as Q plus, then that is called as next state, right? The next state of the T flip-flop, it depends upon the input T XOR with the present output Q. Similarly, for SR flip-flop, the characteristic equation, it goes like this: Q plus is equal to S plus R dash into Q, right? So R dash into Q. That will be the characteristic equation of SR flip-flop. Similarly, for JK flip-flop, Q plus depends upon J into Q dash plus K dash into Q. These are the directly available characteristic equation. You can use any one flip-flop in order to design a state table and its graph. Right. After knowing the characteristic equation, the next is to plot the next state map for each flip-flop. Right. So you, by considering the present input and by considering the present output, you should need to design the next state by mapping for each flip-flop. This is the third step. The fourth one is combine these maps to form the state table, such a state table which gives the next state of the flip-flop as a function of their present state, and the circuit inputs is frequently referred to as a transition table, right? So once if you plot the next state, or if you map the next state for each flip-flop, then you can able to decide how the state table will be generated, right? So how the state table will be generated and how frequently it has got its transition table, right? These are the four steps where I can design the state table, right? So we have a simple explanation for that, right? So I have considered one example that is supposed to be called as Moore model, right? So Moore model, it depends, it decides, that is we have got totally two conditions here. One is called as Mealy model and another is called as Moore model, where Moore model, it is used to have a good example under state table operation, right? So it says that derive the next state table for the circuit of the following figure, right? So here we can see through that we have considered only a simple D flip-flop, where D flip-flop, we know that for the D flip-flop will have its output, whatever input D I have provided, so that will be the output for the D flip-flop. So simple D flip-flop I have considered for having the Moore model operation. So this Moore model, it says that it activates based on the present input and the present output, it will decide the next state, right? So it will decide the next state, right? So hence the diagram is found to be very easy. The Z output will be having the combination of A, X or B, right? So you can able to see that the output Z, it completely depend upon the exclusive OR operation of A, exclusive means A exclusive OR with B. See here, this will be your A and this will be your B. So Z, the complete output of Z equation will be available as A exclusive OR B, right? But in order to get A, that is nothing but your DA or nothing but your A. So we need to perform the exclusive OR operation as X and B bar, where B bar is the output of the previous state. So that will be considered as the input for FFA. This I call it as FFA and this I call it as FFB. So A output for FFA will depend upon the exclusive OR operation between X exclusive OR B dash. Similarly, in order to get B, you can able to see that it is an OR operation X plus A, right? So hence this logical circuit is given directly without any logic. So, but we need to predict the input and output for this by using the analysis, right? So in a simple way, you know that Q is equal to D because I have taken only a simple flip-flop, that is D flip-flop. So no need to worry about Q and D for the flip-flops. But if I want to provide the DA, then that is DA as an input, then I need to get the data from X input and B dash input and B dash as an input, right? So both data, it should be XORed in order to decide the DA, and whatever DA is there, the A will be following with that, right? So hence DA will be equal to X exclusive or B dash. Similarly, DB or nothing but B is equal to X plus A and Z will be equal to A plus B. Okay, so this will be the characteristic equation, that is a flip-flop input equations and output equations. Okay, the next state of the flip-flop will also matters with that, where A I'll be calling it as A plus and B I'll be calling it as B plus, right? Hence, by the help of the next state, that is a state graph, that state table, I can able to write it as A plus will be equal to X exclusive or B dash, right? So this will be DA, means the signal will be present over here. Then based on the present input, and the clock, we are going to decide the next state. That is what your Moore model. So I can able to say that A plus will be equal to, so if I want to generate A plus, then again the same version, I need to perform exclusive OR operation between X exclusive OR B dash. Similarly, in order to get B, I need to perform the operation of OR gate between X and A. So B dash, B plus, that's the next step, B plus will be equal to X plus, right? So in this how you can able to find the next state equation, right? So by seeing through both the equations, we can hardly found that in the first equations, we will write for dA and dB. In the next state of equation, we will write the same equation with respect to A plus and B plus. Okay, so that is your present state and the next state of the flip-flop, right? The state table, it shows like this. As you people know that there are two inputs now, A and B, right? So A and B are the two inputs. So I will be having totally four sequences, 0 0 0 1 1 1 and 1 0, right? And X will be acting as a controller here, right? So X will be acting as a controller here, right? So where A and B are found to be the data for this, right? So when X is equal to 0, so this is how the state table manipulates here. When X is equal to 0, for the present state 0 means for the present state of input 0 0, when X will be equal to 0, then it will move to the state called as 1 0, right? So then it will move to the state called as 1 0. Similarly, when the present state is 0 0 and if X is equal to 1, and if X is equal to 1, then it will move to 0 1 condition, then it will move to state 0 1 condition. Okay, similarly, if the state of the present state, if the present state is what found to be 0 1, that is the second sequence in the truth table, in the state table, then under which when X is equal to 0, it will go back to 0 0, and when X is equal to 1, it will reach to 1 1 state. When the present input of A and B is 1 1, and if I provide X is equal to 0, then it will be moving towards 0 1, and if X is equal to 1, and when the present state is 1 1, and if X is equal to 1, it will stay in the same state as 1 1. Similarly, when the present state is 1 0, and if I provide X is equal to 0, it will move to the fourth state, that is 1 1, and if X is equal to, and if A and B is equal to 1 0, and then I make that X is equal to 1, then it will move to 0 1, and depending upon that, the output will be predicted, right? So the output will be predicted here, right? Now, if I want to make it as a state graph, so then I need to check out this particular table, right? So I will be writing a state table for this by using a pen, right? So by using a pen, right? So just like I will be using a pointer here. Okay, I think, okay, see, I will be like noting a point like this. I have got S naught, okay? I have got S naught, where I will treat it as A as 0 and B as 0. This will be the condition, right? So I will make it as S1. This is a state graph from the state table, right? So from this part, I'm going to write the state graph here. So if I will call it as S1, then I will make it as a 0 1, because S1 is a state when the inputs A and B, right? This is your A input, okay, and this is your B input. So A is equal to 0 0 and AB is equal to 0 1. It is called as S1 state. Similarly, this is what's supposed to be called as S2, where the inputs A and B are found to be 1 0, and similarly I have got something called as S3, where A and B is what found to be 1 1. Okay, so this entire thing I will make it as one state. I'll make it as one state. This is the second state, okay, this is third state, and this is fourth state, right? So in order to move from one state to another state, there is an activation key which is supposed to be called as X. Okay, see, now analyze the truth table. I have taken A and B as 0 0, correct? What happens when X is equal to 0? Where it will move to the condition called as 1 0, right? So where is that 1 0? 1 0 is what found to be here, okay, right? So now I need to activate the thing called as when X is equal to 0, correct? So when X is equal to 0, with the available state 0 0, it will move to the state 1 0, correct? Next, similarly, what happens for the same input, what happens for the same state if I have X is equal to 1? Thank you. right? So if I have x is equal to 1, right? So for where to where it will move to the state called as 0, 1, right? So hence this will move to the state called as 0, 1 when x is equal to 1, right? So when x is equal to 1, right? So this is what a kind of state transition with the help of the state table by writing the state graph. Okay, now see, assume that now the state is at 0, 1 condition. Okay, now the state is at 0, 1 condition. What happens when x is equal to 0? It will move to the previous state. So there will be an arrow mark with the back end direction, and you need to intimate it as x is equal to 0, right? So when x is equal to 0, if the current state is at 0, 1, then it will reach to the 0, 0 state. Similarly, what happens for the same state when x is equal to 1? It will move to the condition called as 1, 1. Okay, so it will move to the condition called as 1, 1 when x is equal to 1. Okay, so by this way, you can able to draw the state graph. This is what's supposed to be called as state graph. This is what's supposed to be called as state table, and the arrow key which indicates the state transition for the graph. Okay, so this is what one of the better example to know about the state table and its operation. Okay, still there are two more cases where you can use these two more cases in order to complete the diagram, right? So this is what's supposed to be called as the state table, right? So hence there are few examples given for a kind of explanation. Try to read it out. So construct a state graph for the shift register shown. X is the input and Z is the output. Is this a Millet or More machine? So that you have to check it out. These are some assignment questions which is not, which is just basically provided as a kind of added advantage, whereas no worries with the kind of examination questions, because this will be not asked much in the examination. This is a kind of added advantage questions, right? So the another state graph based on that another state transition table. So we have one more question called as below is a state transition table with the outputs missing. The output should be x is equal to x, z is equal to x dash b dash plus xb, right? So this is the output equation. So based on this output equation, you have to predict. So what happens to the state transition graph? So how the state transition graph can be possible for the three inputs, right? So now I need to have totally three inputs, A, B, C. How I have used this particular state transition graph in the similar way, you can able to write it out, right? And you have to decide whether is this a Miller machine or a More machine. So and then fill the outputs on the state table and give the state graph. This is what you have to provide, right? So there are few questions which are provided in the slides which I have added recently. So which are the added advantage question, but these questions are not asked in your examination. So please try kindly check it out with the kind of added advantage questions and try to solve this one, right? So and as I said, it's a kind of another the previous assignment questions, the VHDL code for up and down counter. Next, these are the few questions which are asked from your previous examination from the point of module 5. Okay, so this is your module 5 explanation. This is your module 5 explanation. So hopefully I will start with a